Okay, welcome back. So Lemma 3. So Lemma 3 says any subset of a linearly independent set is linearly independent. That is obvious, right? Because if I have a linearly independent set, that means there are no vectors such that I can make a linear combination of any of the other vectors, right? With the other vectors in the set, right? So again, linearly independent set, there does not exist a linear combination of those vectors in the set such that's equal to the zero vector without all of the coefficients being zero. Remember that. But if I have a linearly independent set, what that means, again, another way of saying, is that you cannot find a linear combination of the other vectors in the set that equal that vector. Okay. Now, if that's the case, if I take a subset of that set, then obviously I'm still going to have a set where I can't get a linear combination of one vector of all the other vectors. Well, let me say that I still won't be able to get, if I take one vector out of that subset, I still won't be able to find a linear combination of the other vectors to equal that vector. Okay, so it makes sense in that regard. So let's restate a couple things. So let's restate this. So first, subsets. So keep in mind, subsets preserves independence. Supersets preserves dependence. Okay, those are two of the four cases. Now the other cases we've seen, the other two cases we've seen doesn't hold, right? So subsets do not preserve dependence because we've seen an example of that, and supersets does not preserve independence because we've seen an example of where it gives us both, an example of where both can happen. Okay? Other than that, I'll talk to you later.